the threshold theorem, for those in the audience who doesn't know, states that error correction can only be achieved if a certain required manipulation, quantum manipulation, can be performed with very low error, so below a certain threshold, therefore threshold theorem. Like when theorists calculates this threshold, what contributes to it, and how is it calculated? Is it difficult? Does it take into account these experimental parameters, like measurement time scales and all these trade-offs, and how does it take a lot to calculate it?
John, you've calculated it.
Boy, I calculated it. When David Pullen was a postdoc at Caltech, and sadly he's no longer with us, but one day he kind of took me aside and he said, "Why are you always proving threshold theorems? Do we have to beat that to death?" But there were a number of questions of principle that in those days I was trying to address by proving threshold theorems under different conditions. So first of all, what do you need to make it work at all if you're going to have a threshold? Well, you need to do parallel processing. You need to be able to perform logic in different parts of your device simultaneously, so you can take care of the errors that are occurring at some constant rate throughout the device. And you need the noise to have nice properties. In particular, of course, it's got to be weak enough. That's the whole point of the threshold, that there's some level of the noise such that when the noise is below that level, error correction in principle can make logical error rate as small as you please, so you can compute for as long as you want. But it also has to be sufficiently uncorrelated. The error correction methods that have been most extensively studied, and for good reasons of principle, don't work well if there are errors that act collectively on many qubits at once. And then the details, the answer to your question about how hard it is, depends on what you want to assume about the noise. So what we tried to do in our work was, assume as little as we could get away with it. But we always had as an essential ingredient in the noise model that, it was sufficiently local and the correlations in the noise were sufficiently suppressed. And if you have, so we considered models where, the noise acts on qubits one at a time or two at a time or many at a time. And the condition that you need on the noise that acts on the qubits, two at a time or three at a time, is a lot more stringent than the condition on the noise that acts on the qubits one at a time, which I guess isn't a surprise. But it was interesting to work that out. Another issue is coherence. Often people ignore the coherence in the noise. The way we usually think about noise at a fundamental level is that, there's some interaction between the system and the environment that's itself described by some Hamiltonian. And so the errors are not the way we often like to model them for simplicity, exactly described stochastically. I spoke of an error rate of 1% or 10 to the minus 3. So implicitly, it's like the gate is either good 99 times out of 100, or with probability 1% it's bad. That's a bit of a oversimplification as well. So if you want to allow the noise to be coherent, then that also enters into the threshold calculation and makes it more complicated and also more pessimistic.
Yeah, let me chime in. I mean, there's also sort of one of the questions here is sort of, I have a problem that I'm working on where I'm trying to do a threshold calculation actually on my other window over here. So one of the interesting things is, they're just the different assumptions you're making this. And sometimes you're trying to prove thresholds, like John was talking about. Sometimes you're also just trying to numerically sort of get a handle on where things are and what the trade-offs are. And there's sort of a hierarchy of hardness in understanding this, right? And there's sort of like very simple noise models where it's easier to do this. And then as we get more complicated, we, I think, have less understanding of what happens. And there are likely things hiding there, right? In fact, I mean, I saw one in the last year, which is that There are codes that when I first started, I worked on these things called decoherence-free subspaces. And there was a code that I worked on as well. There's an error correcting code. And it's natural to look at these things on on a 3x3 grid or a 5x5 grid, distance 3, distance 5. Distance 4 is weird. It's like in between those two. Distance 3 can correct 1 error, distance 5 can correct 2 errors. Why would you do 4? Well, it turns out if you look at the 4x4 case, these codes actually had in a particular choice of sort of what people call gauge that they can be robust to a coherent error. So one of these errors that John described as not being described by the stochastic thing. And in fact, it's robust to sort of a collective, you think about a collective magnetic field across this 4x4 patch. If it's in one particular direction, it's sort of protected. And that's really fascinating because that's an example of a coherent error that you're sort of like, it won't be 100% uniform. So you won't be 100% perfective, but you might, take an error rate from that process that's, large and get it down by a factor of 100, right? That would be a major improvement. And that can then impact the design of your qubits. Different architectures may have that problem, and now it may be less of a problem for them, right? So understanding places where how the noise model interacts with the error correcting code is hard. And one of the issues is just, it's very hard to simulate those systems. Very famously, I love this paper, but I don't know if many people know it. The late David Poulin had a paper which basically said, like, his argument was essentially like, you need to run the quantum computation to actually figure out what the right way to deal with the errors are. And maybe that's true, I'm not sure, but that's a fascinating sort of world that we get to the point where actually it's really hard to even simulate this, and maybe we have to just go and try it and see what's going on. It's hard for me to understand that.
I wanted to make one other point of principle, which I neglected to make a minute ago, which is what's essential for having a threshold. An additional thing that's essential is you need to be able to refresh the qubits, or in some way or other flush entropy out of the device. You might just do it by measuring the qubits and storing a classical record of how you measured them, but at any rate, if you're thinking about how to make quantum computing fault tolerant, you always have to have in mind how you're going to remove the entropy, and that enters into a threshold calculation. Also, I guess another thing we haven't mentioned is leakage. There's a type of error where the qubit just goes off to never land for a while out of the encoded space. And that happens in real devices. And so if you're going to deal with it, you have to have something like a reset after leakage. And, that can also affect the threshold. So the story can get complicated.
The interesting thing about the leakage thing that I always love is, like, counterintuitively, what you really want is a place to put your quantum information that is really bad at storing it, right? Like, you really want to flush it as quick as possible. And I think sometimes we get caught in a thing where we're only trying to improve these base decoherence things, not thinking like when we engineer it, we actually need a place to dump it, right? And we've seen examples of that where if you don't have a fast reset and you just let your system relax back to 0, you can improve the lifetime of your qubit. But then that slows down your computation, because if you're just letting it relax back, right, you have to wait longer because you've got a better qubit, right? So sometimes it's good to have really gnarly bad things in your system, but you need to be able to switch them on and off, of course, and that's part of the challenge, right? But keeping it cold is important.